Good evening once again. Welcome back to my YouTube channel. In today's topic, we are going to look at cardiac excitation contraction coupling. Having finished the action potential, cardiac action potential, and then we saw depolarization and relaxation. Now we are going to incorporate them into the cardiac excitation contraction coupling, or we are going to see how the depolarization or the action potential leads to actual contraction. Whenever there is an action potential, the end result of an action potential should be contraction, and then after contraction the muscle should relax and then prepare for the next action potential. So in today's topic, in today's talk or lecture, we are going to see how contraction happens in the cardiac muscle. Elsewhere in physiology, general physiology, there is excitation contraction coupling of skeletal muscle. It is almost similar, but only a few differences, and we shall be highlighting those differences. And then within the talk, we shall talk about the clinical or applied physiology. That is, which drug that can work and where it will work. Yes, we start. Here above, it is a drawing showing a cell, that is a cardiac myocyte. I'm going to be labeling. I drew this one earlier on so that we shorten the duration of the lecture by not drawing. So that's why I drew it already. I'm just going to be labeling. This is a structure of the cell membrane. We are using the full mosaic model of a bilayer, and these are the two layers of phospholipids. These are hydrophilic, hydrophobic tails. They form a layer inside which is hydrophobic. Now within the membrane, we can have proteins, different proteins that span the membrane. One of them, it is this in orange. Another one is in blue. Another one is in pink mixed with blue. Another one is in green, and then another one is in pink. Same here. And then these are the myosin filaments. This is a contractile machinery of the muscle. This is in contraction, and then this one is in relaxation. So what is the exterior? The exterior component, extracellular fluid, is this side. Extracellular fluid is there, and then intracellular fluid is the one inside here. So this is the cell membrane. Outside we have extracellular fluid, inside we have intracellular fluid. When an action potential comes, it moves across the cell membrane and activates everything. Wherever the cell membrane dips inside the cell, that component or that section, we call it the T-tubule. This component, this section here, where the cell membrane dips inside the cell, it is called the T-tubule. The T-tubular system. So when an action potential, remember we drew this one, we assume it's a ventricular myocardial cells, and this one is going to be its action potential. We say this is phase 0, phase 1, phase 2, phase 3. 0, 1, 2, and then 3. Those are the phases. So this from here to here, this is depolarization until this point, depolarization. And from here to this point is it repolarization. So at depolarization, remember what we said, that calcium channels, they are open here in phase 2. Here we have potassium channel, here we have calcium, and then here we have potassium again, and here we have sodium. Sodium is only in depolarization, not contraction, but calcium is both in depolarization and contraction. When a skeletal muscle, calcium is in contraction, but in heart muscle, it is in both depolarization and contraction. So this is what happens. We know that inside here, extracellular fluid, we are having a high concentration of calcium. Yeah, and when the action potential arrives, the first one to open, they are the sodium channels. The next one, they are the first potassium channels, and causing a depression in voltage, partial repolarization. And then next one to open, they are slow calcium channels. And what are the slow calcium channels? It is this one. The slow is called the L type calcium channel. It has its name. The special name for it. It is a dihydropyridine receptor. This is a receptor that is it is a voltage gated. Whenever voltage reaches at a certain point here or here, the slow type calcium channels, these channels, they start opening. And whenever they open, what happens? Calcium, since it's high concentration here, it enters inside. It enters inside. Yeah. When calcium open from the extracellular fluid, it enters, interacts with this guy here, and the rest goes down to the contractile machinery. Now, in the cardiac muscle, there is direct communication between extracellular fluid and intracellular fluid via the dihydropyridine receptor. Whenever it opens, the extracellular fluid communicates directly with intracellular fluid, and that is how calcium can pass and enter intracellular fluid. Since it's low there, it is low intracellularly and more extracellular, so it will travel down its concentration gradient inside. This process is so important in cardiac cells. Here inside also we have calcium. This one is the guy called the sarcoplasmic reticulum. This one is called sarcoplasmic reticulum. Same apply this side, is the same guy, sarcoplasmic reticulum. So whenever calcium comes, one thing that it does, it interacts with this gate here, and the name of this gate is, the gate has a name. It is a ranodine receptor. Ranodine receptor. I'm using short forms, they are known. Ranodine receptor. So this ranodine receptor responds to calcium. Whenever calcium comes, it opens. Like at this point here, it is blue. In the blue section here, it is blue here. In relaxation, it is closed. Relaxation, it is closed because in repolarization, this slow type calcium channels close. So when they close, there is no more calcium to interact with it. So whenever there is no calcium to interact with it, it closes. Here in the relaxation phase, it is closed. Again, we said in this phase, encapsulate everything. We have relaxation, and then here we have contraction. Yeah, two phases we are capturing. So for contraction, when the depolarization, the action potential comes, depolarization happens first. Depolarization opens the voltage gated L-type calcium channels. You can write as dihydropyridine receptor. The result is entry of calcium from extracellular fluid to intracellular fluid. Calcium entering into the intracellular fluid interacts with the ranodine receptor on sarcoplasmic reticulum, which opens or changes the conformational change of the ranodine receptor. Whenever the conformation change, it opens, and when it opens, this one happens next, that calcium from inside, it moves out. Calcium from sarcoplasmic reticulum, when the ranodine receptor open, it moves out into the sarcoplasm. Whenever it moves into sarcoplasm, know these are contractile proteins. These are contractile proteins. So we have the Z line here. This is the actin, and then this one is the myosin, black. The one in black is myosin. Now around the actin we have other proteins. The actin we have other proteins. Two of them, they are there. Two proteins are there. This one is in black surrounding the actin. So one of them has to be tropomyosin, and another one in blue is it troponin. So when calcium comes, one from sarcoplasmic reticulum, two from extracellular fluid via the L-type calcium channel, it will interact with troponin. So when it interacts with troponin, all these two proteins, they are surrounding the actin. So when it interacts with troponin, troponin leads to change in the shape of tropomyosin. When tropomyosin is there on actin, it is blocking. This actin has the active site or the binding site. Actin has the myosin binding site. This is in general physiology. Whenever calcium binds to troponin, tropomyosin changes configuration because they are wrapped together. Changes configuration. Whenever changes configuration, it opens the binding site, the myosin binding site, because myosin with these spikes, it has to bind on actin. So if calcium binds to troponin, this one will change its shape, and the binding site, myosin binding site on actin will be exposed. And the next thing is myosin head to attach into its binding site on actin. And now we initiate a power stroke, and then ATP hydrolysis happens, a power stroke happens. Now it has to leave, and then when it leaves, it's still leaving, it needs the ATP hydrolysis. When it leaves, it attaches in another place. Same process happens. I'm not going to say because it's in general physiology, and so on and so forth, until when the action potential fades. Now, why do we have, because in the other general physiology, we don't have this process. For skeletal muscle, this process is not there. Calcium entering from extracellular fluid into intracellular space, it is not there. But now here it is there. Why do we need calcium to enter here? Why do we need calcium to enter directly from extracellular fluid into intracellular space? One, the sarcoplasmic reticulum in cardiac cells, it is not well developed. Why? Calcium from ECF, extracellular fluid. Why do we need it? Sarcoplasmic reticulum in cardiac cells is not well developed. Is not well developed. So calcium stored inside here, it is not enough. So calcium stored inside here, this is a store for calcium even in skeletal muscles, even in cardiac muscle. But in cardiac muscle, it is not well developed, so it cannot store enough calcium for contraction. For a strong contraction to occur, we must supplement with calcium from extracellular fluid. We must supplement with calcium from extracellular fluid. So that's why it comes here, and also the one released from sarcoplasmic reticulum, it also comes here as a contraction machinery. And when you see here, the contraction has happened. H zone is not seen even. No? So it's not well developed. So the strength of contraction depend on calcium concentration in ICF, in intracellular fluid. The strength of contraction of a cardiac muscle, it really depends on the concentration of calcium in the intracellular fluid. But in skeletal muscle, it is all or none. Calcium is never an issue because it is there inside already. In skeletal muscle, the sarcoplasmic reticulum is highly developed that it can store enough calcium for contraction once an action potential is initiated. But here in cardiac muscles, no. Less developed, less calcium, not enough for generate a strong contraction. We need to supplement with calcium from ECF. So without this supplementation, the strength of the contraction is going to be weak, very weak, and that one will be part of the cause of heart failure. To be part of the cause of heart failure. You understand? So less calcium, heart failure is there, weak contraction, low ejection fraction will be there. We don't need that, and that is when we reach here, you shall see some drugs being used to increase the concentration of intracellular calcium. So this one, it is done now. This is contraction. Contraction, again, what have we said? This is a sliding filament theory happening here. Contraction according to the sliding filament theory. It contracts. So sliding filament theory, you're going to see all the contractile proteins. So another thing, like when we are testing for myocardial damage, one of the troponins, these troponins in myocardial damage, because they can move out of the cell. Again, one of the tests for myocardial damage, like in myocardial infarction, we use troponin T. There are two types of troponins. We have troponin I. Two types are there, trop I and trop T. Trop T is more specific. So in myocardial infarction, to test whether there is myocardial damage or not, we are going to test these troponins, their concentration in peripheral blood. Whenever damage is there of the myocardium, membrane permeability or integrity is damaged or is breached, and whatever next is to intracellular proteins to move out. They move out because the membrane is bleached. They move out, and one of them that they can easily cross, it is the troponins. So when the troponins go out, when the patient comes with chest pain, whatever, we have kits, trop-T kits, we test to check the concentration of troponins in blood. Once they are above the normal limit, and the normal is 0.05 micrograms per dl, I think, less than, it has to be less than. It has to be less than. So if it is more than this, it may be clinically significant, indicating myocardial damage. So if you wait for some time, you may find it is 89. That is too much. Myocardial damage has already occurred. So these ones, they are very, very important in checking for myocardial damage in cases of myocardial ischemia, that is MI and so forth, on and so forth. Other proteins. Now this one we are not going to talk about it because it's also each of diastolic functioning and the dysfunctioning. Now that will be the next part in cardiac cycle. This one here, we shall talk about it. But according to starting filament theory, contraction here has occurred. It has occurred. And when you compare with this one, you are seeing the H zone here properly, but here it is not there. So here, this phase is in relaxation phase, and this one is in contraction phase. So if in contraction all this happens, so in relaxation phase 3, what really happens? Here we start by naming our channels, and this is the closed ranodine receptor. And then this one, very, very important, that it is called Saka, and it has A2. Yeah, this is a pump. It uses ATP. So after contraction, that the action potential has ended, it has reached phase 3. Phase 3 is starting. What really happens? We need to relax. A muscle will never relax when calcium is still inside cytoplasm. If muscle fiber will never relax if calcium is still inside the cytoplasm, or if it is still binding to troponin. If it is still binding troponin, a muscle fiber, a muscle cell will never and ever relax. It will continue in a contractile state as long as ATP is around. So to terminate the contraction, we need to reduce the amount of calcium in the cytoplasm here around the contractile element. And one way to do that is this guy here. We have calcium here, it was binding. This guy is going to pick, it will pick calcium and force it into cytoplasmic reticulum, because that's where it was. Calcium before contraction, before the action potential, it was inside here. And when the action potential arrived, calcium channels opened, interacted with another receptor, calcium went out. It has to go back, and the only way to go back inside here is through this sarcoplasmic, endoplasmic calcium ATPase. Isoform A2 is the one that is found in cardiac muscles. Sarcoplasmic, endoplasmic reticulum, calcium ATPase. SACA2, its job is to pump back calcium into the sarcoplasmic reticulum. Why is it an active process? Because this guy has a lot of calcium inside, so if you want to put more calcium inside, you must use energy. So it is an ATPase because it uses ATP. ATP is the source of energy. So it's an ATPase, it's a pump. pumps calcium against its concentration gradient into the sarcoplasmic reticulum. Another way to take out calcium is by this route. Where it was calcium before contraction, it was outside. Only when the action potential arrived, that's when it came inside. Should we leave it inside? No, we cannot. So calcium has to be taken outside by force. But this guy is called, this guy here, I can label, is called sodium calcium exchanger. It just exchanges. Sodium calcium exchange, that is how it is called in short. So it exchanges calcium for sodium. So what comes in if it exchanges? If an exchange happens, what should come in? Sodium should come in. So here we get sodium from outside. Remember, sodium is more outside, and we bring it inside. It exchanges sodium for calcium. So calcium has moved out and sodium has come in. That's what it does, the sodium calcium exchanger. So that one is finished. So two ways how to eliminate calcium. One, pump it back by force into sarcoplasmic reticulum. Two, take it outside to extracellular fluid through the sodium calcium exchanger. But now a problem you're creating is entering sodium. Should sodium stay inside? No, because here we saw it that it was coming from outside, entering inside at the first phase 0 of depolarization. Meaning, if you allow this one to happen for so long, it will change the concentration gradient. Sodium is naturally more outside and less inside. So if you keep bringing in, you may raise the sodium concentration inside if you don't take it out. But thank God we have this guy that when sodium comes, it doesn't stay inside. It is very fast eliminated outside. It comes inside but very fast eliminated and taken outside. This one is also an exchanger that it exchanges sodium with potassium. It exchanges sodium with potassium. So potassium here comes in. Potassium. So what is the name of this guy? The name of this guy is the sodium potassium pump or ATPase. The sodium potassium pump, the one that you read that it exchanges 3 sodium for 2 potassium, one for maintaining the racing membrane potential or for establishing it. You see the cycle, how it is so interesting. Calcium first has to be eliminated because that is the major goal. We need to relax. 2, you are moving out calcium, you are reducing its intracellular concentration, but creating another problem of sodium. Sodium should not stay inside also, it should get out. So what do we need? Sodium is more. This one is free, doesn't use energy. It is bidirectional. In some conditions it can work, bringing in calcium and taking away sodium. But under normal circumstances, it brings in sodium and calcium goes out. But the sodium should not stay inside, because if it stays, it may change the direction of this guy and it may start bringing in calcium. We don't want that. That is under pathological states. So sodium should be taken out by sodium potassium pump. And here, if no calcium is around, then this troponin and tropomyosin will go back to their resting state, where tropomyosin is covering the the myosin binding site on actin. And when the myosin binding site on actin is covered, then myosin cannot bind to its active site, so no contraction will happen, and that is the relaxation state. Now, what is so important here, these two guys, this one uses energy and this one doesn't use energy. So whenever there's a protein which requires energy, in any case where energy is not being produced, this guy is going to switch off. Whenever a condition comes where the cell is not able to produce the energy that this guy, that energy, I mean ATP, that this guy needs to keep running, it will stop working. When it stops working, what will happen? And this guy is working, he will be bringing sodium inside, and nothing, that sodium will not be going out. This guy works on a concentration gradient, that's why we said it doesn't need energy, it's free. Works on the concentration gradient of sodium, that sodium is more outside and less inside. So it always works to bring in sodium following its concentration gradient, and in exchange, it exchanges with calcium. But if this sodium doesn't go out, then it will stay, reducing the concentration gradient of sodium. So when the concentration gradient of sodium is reduced, 1, it will stop working also. 2, it may reverse the direction, that now it starts working to take away sodium if the concentration gradient inside, has become more than that one outside. It will change the direction and it will start taking away sodium and bring in calcium. That is one of the important things and one of the mechanisms how the digoxin works, is one of the mechanisms of digoxin. Digoxin is a drug used in heart failure. Heart failure, that is, in heart failure we have reduced ejection fraction, reduced EF. So in heart failure with reduced ejection fraction, what do we assume? We assume the reason why there is reduced ejection fraction, the heart contractions are weak. The contraction of the heart are weak. Remember here we said the strength of a contraction depends on the amount of calcium inside. So if you want to make sure that calcium increases inside, what do? Interrupt this guy. Interrupt the sodium potassium ATPase. So the digoxin switches off the sodium potassium pump, and when this one is off, then sodium will stay inside here, reducing the concentration gradient on which this sodium calcium exchanger works. If the gradient reduces 1, it may stop working. When it stops working, calcium will remain inside here and more will be pumped into the sarcoplasmic reticulum. 2, it may change the direction, that instead it brings in calcium. When calcium is being brought back, now that one ensures that the calcium content inside the cell, it is more, and now the cell at the time of contraction, it will generate a very, very strong contraction, and now very able to eject a good amount of blood outside into the alveoli. Why does it depend on calcium? Because the strength of contraction depends on how many myosin active sites are open where myosin can bind, or how many number of cross bridges are formed. If few, in case when calcium is few, only a few will open. If calcium is much, many will open. If many open, the number of cross bridges formed increases. The number of cross bridges is directly proportional to the strength of contraction, and that's what we need. So we give this drug in heart failure to increase calcium content. Why? It blocks sodium potassium ATPase result increase in intracellular sodium content ICF. And what is the next result? It is decreased function of sodium calcium exchanger, and the final result is increased intracellular calcium content. That is how it works. That's how digoxin works. Another one too, because another clinical consideration, because this one works, it can, when it switches off, it uses ATP. Anything that reduces ATP generation is going to switch off this one. One is ischemia, myocardial ischemia, like blockage of coronary arteries. So in the culprit region, the cells will have non-functional sodium potassium ATPase, and all of them will be having an increased concentration of calcium inside. When calcium inside increases, because of ischemia, it contributes something called reperfusion injury. I'm not going to go far with this one. It contributes to something called reperfusion injury. What is reperfusion injury? When there's blockage, like for example of coronary artery, like LAD, and then you open it, in spite or despite of you opening it, the myocardium may continue to deteriorate, or the function of myocardium may continue to deteriorate. The damage may escalate. 1. Reactive oxygen species. 2. Microvascular dysfunction. 3. Inflammation. 4. Increased intracellular calcium. With ischemia, there is a disruption in calcium handling. That is a term, calcium handling. Who is involved in calcium handling? 1, 2, and 3. 1, 2, majorly this, they are directly involved in calcium handling. This one, the most important, that if it fails to pump calcium back into sarcoplasmic reticulum, this one, even if it works, it will be slow. So calcium inside here will remain much. Mutations that affect this gene that encode this protein, if it is a loss of function mutation and this guy is not functioning well, calcium will always be more intracellularly. And whenever it's more, remember we said a cell will never relax when calcium is still inside the cytoplasm. Otherwise, if it's there, it will be binding, it will interact with troponin. Whenever troponin is get in touch with calcium, tropomyosin open. So if the concentration here is much, like in loss of function mutations of SACA E2, that cell will always undergo small contractions, and whenever small contraction, or the cell will never rest. Whenever a cell will never doesn't rest, one big topic can happen, like diastolic dysfunction. Like, for the heart to work, it must get enough time to relax. And for the heart, we call it diastole. Systole is contraction, diastole is relaxation. And in diastole, we shall see next topic in cardiac cycle, what happens in diastole. Diastole, proper diastole can only happen when the cell fully relaxes. Fully, like here. Fully relaxes, and that's when the heart muscle can stretch to accommodate a good volume of blood. If these cells, they have not rested because calcium is still inside, some few cross bridges are formed, it will be restricted. and that heart will never get or allow enough blood to enter. So diastolic dysfunction, this one can cause. But since it's a mutation, the treatment can only be gene therapy. But I think nothing has been discovered now or approved. Everything is still in trials. Otherwise, people have diastolic dysfunction because of a non-functioning SACA-A2 protein. Now, some terms that I didn't say, we have calcium-induced calcium release, calcium-induced calcium release. You search about that one, and then voltage-induced calcium release. What is the difference? Voltage-induced calcium release in skeletal muscles. These ones are also voltage sensitive. Whenever voltage comes, like it senses a voltage in skeletal muscles, this one is directly coupled, mechanically connected to ranodine receptor. At a certain voltage, it will change the conformation, and this change in conformation, because they are mechanically linked, the change here will affect the change, the shape here. So when the shape here changes because of this one, it will open and calcium gets out, and that one is called voltage-induced calcium release, because it is in response to a voltage. But in calcium-induced calcium release is at this, like this situation. Voltage, it senses the voltage, it opens, calcium enters, and it will be calcium that is open this one, ranodine receptor, not the physical interaction between these two. So this one is calcium-induced calcium release. When the calcium interact here, it will cause more calcium to be released from sarcoplasmic reticulum. I think that is one of the basic, very basic we have seen, and some few clinical or applied physiology. And thank you for that. Today we have used one page only and summarized most of the important things. Yeah, thank you. See you next on Saturday. Saturday it will be, this one was general physiology. Saturday we shall go back to our ECG electrocardiogram. Yeah, thank you.